Often, one of the most important statistics that we consider for a random variable is the expectation of the random variable. So when the expectation exists, we equivalently call it the mean or the expected value. And it is defined in the broadest sense as the sum of two integrals. The integral of the distribution function of x, from negative infinity to 0, plus the integral from 0 to infinity of the complementary distribution function of x. As you know, the complementary distribution function is nothing but 1 minus the distribution function. So the expectation exists if both of these intervals are finite. The expectation exists and is finite. If only one of the integrals converge, the expectation can still said to be, is still said to exist, but it is infinite, either positive infinity or negative infinity. If neither integral converges, the expectation is said to not exist. Right. So in the special case, this expression reduces in the special case when the random variable x is positive. The definition of expectation reduces to simply the integral of its complementary distribution function. In other words, the probability that x is bigger than x integrated from 0 to infinity. This is a useful equality that we will use later on in the course. This is true for random variables that are positive valued. Now, for discrete random variables, in the discrete case, the expectation is a summation. So what do you mean, discrete case? For some values, countable values ai, probability x equals ai sums to 1. So in that case, the expectation of x is simply given by a weighted average of these ai's, where the weights are the probabilities. ai, px of ai. So it is a weighted sum, and this is essentially the center of gravity of the probability mass function. Okay? In the continuous case, where x is a PDF, okay, the expectation is given by the integral version of the same expression, minus infinity to infinity over all real numbers, that is x times the density at x dx. Here we are taking the mean of the density function. We're finding, again, the center of gravity of the density function. For example, in the case of a Gaussian distribution at with mean mu, it is very easy to see that the center of gravity of that distribution is at mu. So mu is the mean or the expectation. Now, as a consequence of these definitions, notice that all of these definitions involve integration or summation. Expectation is by its very definition a linear operation. So the linearity means that when we combine ax plus by, or in fact any number of random variables linearly, the expectation of the sum is a times expectation of x plus b times expectation of y. This is a fact that we will use often throughout the course.